For years, hybrid cars were treated like a temporary compromise. Not fully electric, not fully gasoline, just an awkward transition technology people assumed would eventually disappear. But something unexpected happened. As modern gasoline engines became smaller, more turbocharged, and increasingly stressed by emissions regulations, hybrids quietly started solving mechanical problems. Traditional cars were struggling with more and more every year. And the deeper you look into modern engine engineering, the more that starts making sense. Modern combustion engines operate under extreme pressure compared to engines from the 1990s or early 2000s. Downsized turbocharged engines now regularly produce power figures that would have required much larger displacement 20 years ago. A modern 1.5L turbo engine can easily produce over 180 horsepower. The problem is that extracting that much power from a small displacement engine creates enormous thermal and mechanical stress. Higher cylinder pressures, increased combustion temperatures, turbocharger heat, direct injection carbon buildup, low-speed pre-ignition risks, tighter oil tolerances, and more aggressive emission systems all increase long-term wear potential. Engineers have become incredibly good at making small engines powerful, but physics never stopped existing. That's one reason many modern engines spend their entire lives constantly moving through inefficient operating ranges. In city driving, especially, gasoline engines are terrible at low speed efficiency. Every stoplight forces the engine to repeatedly drop RPM, rebuild load, inject extra fuel, and move a heavy vehicle from zero again. That cycle creates wasted energy, increased brake wear, unnecessary idling, and higher fuel consumption. Traditional combustion engines are actually most efficient under stable load conditions, not stop-and-go traffic. And that's exactly where hybrids change the equation. A hybrid system allows the electric motor to handle the least efficient part of driving, low-speed acceleration. Electric motors produce maximum torque instantly from 0 RPM. That means the gasoline engine no longer has to constantly struggle through inefficient low-speed operation every few seconds in urban traffic. In many hybrid systems, the gasoline engine can remain off entirely during low-speed movement, startup, parking maneuvers, or traffic crawling. That dramatically reduces cold start cycles, idle time, and transient load stress. And cold starts matter more than most drivers realize. Studies in tribology and engine wear have shown that a significant percentage of engine wear occurs before oil reaches optimal operating temperature and full circulation pressure. Reducing unnecessary cold starts directly affects long-term durability. This is also why many hybrid engines age differently from conventional turbocharged engines. Toyota's hybrid systems are a perfect example. Most Toyota hybrids use naturally aspirated Atkinson cycle engines rather than heavily boosted downsized turbo engines. The Atkinson cycle keeps the intake valves open longer during part of the compression stroke, reducing pumping losses and improving thermal efficiency. The trade-off is lower low-end torque. But hybrids solve that weakness instantly because the electric motor supplies torque exactly where the gasoline engine lacks it. So instead of forcing a tiny turbocharged engine to constantly operate under high boost pressure, the hybrid system distributes the workload between two completely different power sources optimized for different conditions. And the reliability numbers behind this strategy are difficult to ignore. Toyota Prius taxis in cities like New York, Vancouver, and Dubai have repeatedly exceeded 300,000 to 500,000 miles on original hybrid drivetrains with surprisingly low mechanical failure rates. Part of that durability comes from the eCVT system itself. Unlike traditional automatic transmissions with multiple clutch packs, planetary gear changes, valve bodies, and aggressive shift shock, Toyota's hybrid Synergy drive uses a planetary gear set combined with electric motor control to create a continuously variable power delivery system with remarkably few moving parts compared to conventional automatics. Fewer hard shifts means less drivetrain shock. Regenerative braking also dramatically reduces brake wear because the electric motor itself slows the vehicle while recovering energy back into the battery. Some hybrid owners report brake pad life exceeding 100,000 miles under normal driving conditions. Now, obviously, hybrids are not perfect. Battery degradation is real, especially in extreme climates. Additional electrical systems increase complexity and long-term battery replacement costs can become expensive depending on the model. Hybrids also carry extra weight due to battery packs and electric motors, which can reduce efficiency advantages during sustained highway driving where regenerative braking matters less. And not all hybrid systems are engineered equally. Some manufacturers rushed poorly integrated systems into production during the early hybrid boom and created reliability problems of their own. But the broader engineering logic behind hybrids is much smarter than most people initially realized. Instead of forcing one engine to perform efficiently in every situation, hybrids divide the workload strategically. The electric motor dominates where combustion engines are weakest, while the gasoline engine handles sustained cruising where internal combustion still performs extremely well. In many ways, hybrids succeeded not because they replaced gasoline engines, but because they reduced the situations where gasoline engines perform badly. And as emission standards continue tightening while consumers still demand reliability and fuel efficiency, that balance is becoming harder for traditional powertrains to ignore. And maybe that's why hybrids survived while so many people predicted they would disappear. For nearly 2 decades, the conversation around cars became extremely polarized. Gasoline versus electric, old technology versus new technology. But hybrids quietly occupied a middle ground that turned out to be far more practical than many expected. Snorts because in the real world, engineering is rarely about ideology. It's about compromises, efficiency, durability, and solving problems under real operating conditions. What's interesting is that many of the advantages hybrids offer are almost invisible to drivers. Lower thermal stress, reduced idle time, smoother load distribution, less brake wear, more efficient urban operation. These are not flashy marketing features, but mechanically they matter enormously over hundreds of thousands of miles. And the industry itself seems to recognize that now. Even manufacturers that once pushed aggressively toward full electrification are slowing down and reinvesting heavily into hybrid platforms because consumer demand and infrastructure realities turned out to be more complicated than expected. And maybe the most important lesson is this: hybrid technology was never really about replacing combustion engines overnight. It was about correcting some of the biggest weaknesses modern combustion engines developed as efficiency standards became harder and harder to meet. In many ways, hybrids didn't succeed because they abandoned gasoline. They succeeded because they learned how to use it more intelligently. Subscribe to my channel.